All right, so we're going to look at how to anti-differentiate a situation when you've got an odd power of sine. So if you've got an integral that looks something like this, we're going to look at how to anti-differentiate this. Now, this is a specific example of any integral in the form of sine to the power of m multiplied by cos to the power of n dx. And this is sort of a special case in terms of us working out what substitution needs to be made in order to be able to simplify the integral and then therefore be able to evaluate definite integrals and to find an antiderivative. So if we think about how we might go about this, basically when you've got an odd power of sine, you're going to use a u substitution of cosine of x. So what we're going to say is, before we get to that, we're going to say that we can re-express this in this kind of format. We need to recall the trigonometric identity that 1 minus cos squared x is equal to sine squared x. So if we just think how we got from that first step to that second step, sine cubed of x is sine squared of x multiplied by sine of x. So if you sort of just separate them out, you can take the first part, sine squared of x, and rewrite that as 1 minus cos squared of x. And then you can see at the end here, we've got that sine of x still there. So altogether, that gives us that sine cubed of x. And then we can see that we've obviously got cos squared of x there as well. What we'll do now is we'll make that substitution to say that u is cos x. And so we end up with this situation. If u is equal to cos x, if you take du dx, you're going to get the derivative of cos, which is negative sine. And then if you just rearrange that for du, you can see that du is equal to negative sine x dx. And so you can almost see that at the end of the integral in the previous step, right? If we were to make this substitution, we can see that it would become this. And let's just take a second to digest that. If we take negative sine of x dx to be du, that's sort of the rightmost part, sine x dx is now du, and then the negatives come out the front. And then we know that if we expand that cos squared x into the brackets, we're going to get cos squared x minus cos to the 4 of x. And so then you can see that that would be u squared minus u to the 4 once you make that substitution. And now you can see we've essentially got something in polynomial form, and we're very familiar, hopefully, with how to compute antiderivatives in polynomial form. So if we go ahead and do that, we're going to get something like this. Hopefully this isn't too surprising. If you take the antiderivative of u squared, you get u cubed on 3, and u to the power of 4 is u to the 5 on 5, and then you just have to account for those negatives. That first term becomes negative, and the second term becomes positive, because it's actually negative inside the integral. So you've got a double negative situation going on. And then when you take an indefinite integral, you have to do plus c. So you end up with this situation as our final answer. And I should say just there that we've just substituted u equals cos x back in. So that is our how we compute the indefinite integral for a odd power of sine. You're basically making a u substitution, and that substitution is u equals cos x. Okay, and so let's have a look at a picture. So if we were to sketch all this out, we can see that that function, sine cubed of x, cos squared of x, has an area of approximately 0.13 in that sort of local region between 0 and its first x-intercept, which is actually at pi on 2, and that's a different question. You can work that one out in your own time. But what we can see here as well is that, if that's going to be the same as the area contained between this pink function, u squared minus u to the 4, between the 2 points that have been transformed. So let me just be clear. So in the first blue function, between 0 and pi on 2, and then in this u function, you're taking those bounds and then you're applying that same transformation, u equals cos x. So cos of 0 is 1, and cos of pi on 2 is 0. So the bounds actually get swapped, which is why we've got this negative out the front, because we know that when we swap the bounds on an integral, it makes it negative. So I was initially confused on why this is still positive, but the situation is because we apply the same transformation to those bounds. And now we're getting into sort of the definite integral a little bit, and sort of properties of that. But I'm hoping you can just sort of get the big picture here that we're making a transformation from X space to sort of U space, and then we just calculate the area in U space, which is a lot easier. And then, yeah, we can find the areas that way. All right. Quite a confusing idea, I think. So if you have any questions, let me know. Good luck with all your studies. If you need any private tutoring, let me know as well. And I'll talk to you soon.